Yeah. So let me continue again. Sorry for the interruption. So we are taking a different perspective here, emphasizing the adaptability of the agents in responding to unforeseen robotic failures or malfunctions that they or their teammates may encounter. So to enhance the adaptation abilities of the agents, our method introduces the team structure, promotes collaboration, and decreases the complexity of the problem by guiding or influencing the agent's strategies. So in a sense, our method fosters a collaborative approach to agents adaptation. Pre-research in multi-agent reinforcement learning can be categorized in three main categories: centralized learning, decentralized learning, and centralized training with decentralized execution, CTDE. Centralized learning utilizes a single controller, and however, it leads to an exponential growth of action space or observation space when the number of agents increases. Decentralized learning, on the other hand, allows agents to solve the problem independently. However, approaches under this category can be vulnerable to non-stationary issues. CTDE addresses the non-stationary issues of decentralized learning through centralized learning during training, and it also overcomes the scalability issues of centralized learning by using decentralized executions. On the other hand, there has been limited research in the context of malfunctioning agents within multi-agent teams. However, some works try to address this problem using dynamic exploration strategies or predicting robot failures by forecasting the movements of other robots. However, here we assume that the malfunctions are unforeseen, so they cannot be predicted. So we came up with a novel framework called collaborative adaptation. It enhances the team adaptation and guides cooperation strategies. And this framework uses CDT paradigm, which is currently considered the most effective approach for addressing multi-agent teams. And the framework incorporates the inter-agent relationships represented as a graph into agents' learning algorithm. Currently, the framework is built upon volley decomposition networks, VDN. However, it is important to note that the framework can also be applied to other CDT approaches. So in other words, we just use VDN here as the learning algorithms for agents. So here you can see an overview of this algorithm on the right. Basically, what you need to know is here that each agent has a deep Q network, DQN, and it uses experience reply like many other RL algorithms, and also it tries to use fixed target networks to emphasize the stability of the agent's prediction network. And it also tries to minimize temporal difference. So, however, the novelty lies in here, in the middle, the green section, which is the relationship between the agents represented as a directed graph. So, in addition to the shared features with other approaches, we integrated this part within our framework. So when agents receive their reward, the team reward will be calculated based on the relationships, based on the team structural relationships. So when we will see the results section, we will see that this enhances the adaptation of the agents as a team. So to demonstrate the effectiveness of our algorithm, we have conducted experiments in multi-agent grid-world environment with 4 agents, as you can see here. So the agent's objective is to consume resources represented as rectangles, and they have 5 possible actions: going left, right, up, down, and staying still. So consuming a resource yields a +10 rewards, while agents are getting penalized with -1 reward per unconsumed resources unless they occupy a resource location which serves as a safe spot. Additionally, they are getting +3 reward when they collaborate to help each other to consume a resource by pushing. So for the malfunction simulation, we introduce a malfunction that prevents green agent from moving. And we also implemented a malfunction trigger to detect the timing of the malfunction and identify the malfunctioning agents by monitoring their rewards. You can see, like, we use two different relational graphs to train our framework. The first one, the left one, is self-interested one, and the other one where all agents are prioritizing supporting the green agent. So before any malfunction occurs, the self-interested graph is used to train the CA-VDN, our framework. As you can see from the results, that there is not much difference between VDN and CA-VDN before malfunctions. So we created the malfunctions when the agents are converged to their optimal policies in first 5K episodes here. So after creating the malfunction which prevents the green agents from moving, we increase the exploration of both algorithms to help them figure out a way to solve the environment again. However, as we can see from this VDN results, that VDN has difficulties converging and finding the new solution for that particular malfunctions. In contrast, when we train the CA-VDN with a relational graph that all agents care for or prioritize supporting the malfunctioning agents, allow to recover from this malfunction as a theme. So here you can see the numerical results for both malfunctions and after malfunction experiments. And as we can see here, as we can observe from here as well, that VDN and CA-VDN before malfunction performs very similarly. On the other hand, the significant difference emerges when we introduce malfunctioning scenarios. So overall, we propose a null framework called collaborative adaptation. And this framework enables agents to recover from the given malfunction, unforeseen malfunction as a team. It facilitates adaptation by incorporating inter-agent relationships into agents' learning algorithm. And as a future work, we aim to conduct extra experiment with more complex environment with different malfunctions, and compare the performance of our method with other state-of-the-art methods. Thank you.
Question from me. In the study you did, the design seems that all the directed graph are pointing in the malfunctioning agent. I'm just wondering if you have a graph that's more evenly distributed, say like everybody's paying attention to everybody. Does the framework still converge back to the optimal policy, or does it just take slower?
No, the weight of the team rewards will be same for each agent, so they won't be able to solve the environment by using the graph that you described.
Okay, so it's then the design of the graph
is important. Yes, exactly.
Do you have any insight on how you can maybe come up with a
that's a great question. So currently we are doing research about that part. Like, we don't want to give the graph directly. We want them to figure out that graph by themselves and solve the environment accordingly. But currently, when we try the earlier experiments takes too much time, and we just giving the graphs as a hyperparameter to the learning algorithm.
Okay, thank you.
Sure.
So the next talk will be iPLAN, intent-aware planning in heterogeneous traffic via distributed MAR by Xiyang Wang. Xiyang Wu, sorry.
Hi everyone, my name is Xiyang Wu, a third-year PhD student at University of Maryland. Today I want to present a work iPLAN that uses the intent-aware planning in heterogeneous traffic with different distributed multi-agent reinforcement algorithm. Yes, the first is our introduction that we design our work from three kind of motivations. The first is the challenges raising dense and heterogeneous traffic that calls for the demand of jointly performing intention inference and trajectory prediction during navigation. And the second comes from the limitation of current data sets that are insufficient in modeling heterogeneity in driving behavior. That this forces us to turn to traffic simulators and use multi-agent reinforcement learning framework to model multiple vehicle agents and their interactions simultaneously. And the last one comes from the fact that no existing multi-agent reinforcement approaches, especially the DTD or distributed execution approaches for joint the intent and trajectory prediction for autonomous vehicles in heterogeneous traffic. And here's our main contribution that we propose a fully decentralized multi-agent reinforcement algorithm that embedded with a classical trajectory forecasting architecture for intent-aware planning in dense and heterogeneous environments. We represent our agents' private incentives with a explicit presentation that includes a behavior incentive that relates to the high-level decision-making strategy that sets the planning sub-goals, and also the instant incentives that represents the low-level motion planning to execute the sub-goals. And we propose a incentive inference mechanism that allow agents to infer their incentives from their opponents solely with their local observations and perform behavior-aware motion forecasting. And next is our methodology. Here's our framework that we model vehicle agents with different kind of behaviors. That's for each vehicle, let's say the yellow, we take the yellow vehicle as the eagle vehicle. Then when they perform the decision-making in heterogeneous traffic, always this has three kind of mind over another vehicle. Let's say the red vehicle here in three aspects, in three kind of aspects. The first one is this current observation that what's the current position and velocity of this red vehicle. This directly comes from the environment. The second one is that what's the most likely action for this red vehicle's driver to take next. This is always related to the red vehicle's behavior mode. For example, whether this vehicle driver is aggressive or conservative. The third one is how should I execute this kind of sub goals and high level actions with our planning results from the behavior incentives so that we can keep safe and keep in track towards the goal. And the relation between the two, the incentives is that we use the behavior incentives to bias the motion forecasting by setting up the planning sub goals with intention awareness, and whereas we use the instant incentive to execute the sub goals for motion planning. And the next is the red block, which represents the behavior incentive inference that we use the historical observation sequences to predict the observation sequence in the next few time steps. And next is the instant incentive inference that we use the current observation and the behavior incentive inference results to generate the instant incentives for trajectory prediction. And when we get the two kind of incentive inferences, we combine them with the current observation and use that for decision making. And here's our empirical results. We perform our experiments over two environments. The first one is the non-cooperative navigation that we use N agents to maximize their coverage over the N landmarks. without any explicit communication or cooperation. And each kind of agents has different kind of like kinematics, and they must dash, reach, and stay at landmarks without any conflicts. We designed two kind of scenarios with 3 controllable agents with different kinematics to reach 3 kind of landmarks, whereas the hard scenario has a extra random uncontrollable agents. And here's the results. We found that our iPLAN, which is the orange curve, that has a higher episode reward than those TTD baselines, for example, the QMix and the MEPPO, and also the DTD baselines like the IPPO in both scenarios. And the other environment we perform our experiments on is the heterogeneous highway, that the vehicle agents should stay correlation free and maintain a proper speed when driving through the heterogeneous traffic. And there is a heterogeneous traffic environment that's both kind of like controllable vehicle agents and behavior-driven uncontrollable vehicles, which are controlled by aggressive model or like defensive model. Both of them are listed in a highway scenario. And we design a scenario with 5 controllable agents and 50 like uncontrollable vehicles, well controlled by behavior models, while the chaotic traffic scenario has more aggressive vehicle agents within the scenario. And this is our results. We found that iPLAN has a better episode reward than those like TTD approaches and the DTD approaches in both marine and chaotic traffic. And we also performed the numerical analysis, which confirms those results. And we also performed the navigation metrics analysis. We found that we use 3 kind of like navigation metrics. The first one is the average speed, and the second one is the average survival time before their correlation. And also we perform analysis over the success rates, that the ratio of agents that survive at the end of each episode. And here's the results. We found that the iPLAN, which is like the last row of each scenario, we found that iPLAN has a better success rate and a longer survival time than all of the other approaches, while iPLAN tend to be conservative in its average speed. Let me check. Okay, this is the animation results to visualize the whole like episode. We found that iPLAN has successfully make all 5 agents to survive in the end. And we also combine the two baselines. The first is the MEPPO. We found that only 2 out of 5 agents survive in the end. And we also cover the results for QMix, and which have the similar performance than MEPPO, which is bad. And thank you for watching. If you have any questions, please feel free to contact me with email, or you cannot see it. And reach out our paper and check our GitHub page. So thank you for any questions.
Any questions from the audience? I have a question. So what does the incentive actually models? Is there like an intuitive way of thinking about it? Because you have both the behavioral and instant one.
Here we take the behavior mode is mostly a stable, which is the most stable variable, that's because we think that a vehicle agents will keep like aggressive or like conservative during the single episode. Well, we use that to bias the instant incentives. While instant incentive we use is more like a latent representation of we learned that from the current observations and the behavior, or considering the behavior mode, and it's more like we use that latent representation to generate the trajectory prediction at few time steps.
So is it more like how much it weighs a penalty on collision, for example, versus other kind of objectives?
Yeah.
So what are your thoughts on actually writing out the incentives explicitly? Like use just analytically all the equations that can represent how much an agent weighs collision to other agents, for example. Is it in the lane? How often does it switch lanes? Instead of using a implicit inverter.
I would say it might be hard because I think the implicit ways may allow for, because it's more like a bit high dimensional ways. It's like it would be able to like simulate a more complex scenarios. The way you feel about it explicitly, like directly give a metrics like how often it's going to change the lane, what's the average speed, for example. It's just considering, because we set up our problem in heterogeneous complex traffic, it would be like limited in if the scenario become more complex.
Okay, thank you.
Thank you.
All right, and next we will have you on
Let's talk.
Functions.
Hello, everyone. My name is Yo-Yo. I'm a postdoc from the University of Texas at Austin. Today, we'll talk about my recent work on active inverse learning in Stackelberg trajectory games. This is a collaboration with Jacob, David, and Wolfuk from the University of Texas at Austin, and Mangharam from University of Illinois at Urbana-Champaign. Now, we're all here today because we love game theory and we want to use game theoretic ideas to build better robots, right? Now, one challenge in game theory, when you try to find a good game theoretic strategies, Nash equilibrium, Stackelberg equilibrium, or correlated equilibrium, is that you have to understand the motivation behind each player. You need to know what are their preferences, what objectives they're trying to optimize, what terms in their decision-making affect their eventual decision. Now, the question I want to ask today is, how can we help our robot friends to figure out a provoking action that provoke informative responses from the opponents that you're interacting with, okay? And this type of interaction could be a zero-sum interaction like you do when you play chess, or a more general sum more general sum nature, non-cooperative interaction as you see in transportation and markets. Now, what do I mean by provoking informative decisions that review each player's objective? Well, let me explain it with a more concrete example that's taken from one of my favorite books, the Harry Potters. So this is a scene from the book/movie from the Harry Potters where there are 7 copies of Harry Potter, and they have to escape, let's say, a bad wizard that tried to kill one of them. Okay. Now I want you to think about this. Imagine that you are controlling the joint action of 7 Harry Potters. Okay. And you know that bad wizard is chasing one of the 7, but you don't know which one. So that's the uncertainty in the agent that you're interacting with that you're trying to figure out right now. Okay, what would you say is a better strategy? Would you ask the 7 Harry Potter to stick together, or would you ask them to split up if you're trying to figure out which one of the 7 is the target of the bad wizard? Split up, right? That's my thought too. And that's the exact intuition that I have when I propose this problem. Splitting up will provoke more informed response from the bad wizard, right? Because you can observe which one of the 7 that this bad wizard is chasing, and because all 7 of them are flying in different directions, you can easily determine what is the preference, what is the objective of the bad wizard. So towards the end of the talk, I will give you some mathematical explanation why this is a good thing to do, and how can we compute a good strategy of this kind that provoke informed reactions from our opponents in the first place. Okay, so that's the goal of the talk. So how do we model the interactions of this nature? Well, building upon the multiple plotter example, I'm going to consider a Stackelberg game. My friend Abu Fazl here has told you all about this in the morning. So this game involves two players. One we call leader, the other one we call follower. Okay. Now for this particular game, because we're interested in decision-making in dynamic environments, we're going to consider both of the players are controlling a dynamical system. Okay, so they're governed by dynamic equations, or consider linear time invariant dynamics throughout this talk. But the leader is optimizing a generic objective function that depends on what the followers will do. Okay. As for the follower, we're going to choose a popular model in the machine learning optimal controllers called the maximal entropy LQR. Right? If you have a control friend, you probably heard about the linear quadratic regulator. It's a workhorse model in control theory. The maximal entropy LQR is a little bit different from the classical one. The only difference here is that we're going to add what we call causal entropy term in the objective function. Okay, so in addition to quadratic cost objective function on the trajectory of the system, we're going to also consider this entropy term. And this term captures the bounded rationality in decision-making. Basically, it captures noisy behavior. Okay, when you try to model the decision-making of human beings, they often make suboptimal choices, but the probability of taking that choice decays exponentially as you move away from the optimal one. And when you optimize this objective with the entropy in it, you get exactly a distribution trajectories that has this property. Now the game happens when because the leader's objective function will depends on what the followers will do, and the follower will take whatever the trajectory the leader decides and use it as a reference mapped by this green matrix M. Okay, so this is the basic setup we can consider. Now, the learning problem happens when the leader does not knows that the follower's objective function depends on the matrix M, and this matrix M comes from a finite number of candidates. Okay, so we're going to make an assumption that the leader, in this case, knows that. In the hard part example, the leader knows he's chasing one of the seven. I just don't know which one. Or in more a generic setup, you can say, well, I have already, based on prior knowledge, built all these hypotheses that could possibly explain the behavior of a player that I don't know today. And I'm trying to figure out which one of the hypotheses best explain the behavior. Okay, so this is the problem we're trying to solve. We're trying to help the leader to figure out a good trajectory that once the leader chooses this trajectory, the follower's reaction to the leader's trajectory is going to tell us a lot about which M is most likely to explain its behavior. So let's think about a little bit about this inference problem. What makes it different, or what makes it hard? The good thing about LQR or maximal entropy LQR is that you can write down the follower's response in closed form. You can write down the distribution of this trajectory. It is satisfied this set of dynamic equations, both the mean and variance of the Gaussian distribution. Now, if, for example, the distribution of the trajectories under different hypotheses are very close to each other, like the one upstairs, you have a very hard time to distinguish one hypothesis from the other one, right? If you observe one of the trajectory and it's actually sampled from the orange pile, if the orange and blue and the piles are very close to each other, you have a very hard time to tell which piles come from. Versus if the distributions are very different from each other, then it's very easy to tell which hypothesis is governing the distribution of the trajectories. But the cool thing is that this difference is not set in stones. So the follower's response under different hypotheses all depends on what the leader's trajectory is. So there's one X sub L term in that equation that determines how these distributions differ from each other. And you can measure this difference using, for example, KL divergence. And that's our choice to measure difference. So our idea is to I want to help the leader design this trajectory that maximizes the difference in the trajectory distribution once the follower sees the leader's decision. Okay, so we try to end up in the scenario downstairs and not the scenario upstairs. Okay, so what does it look like mathematically? Well, we have the leader's decision, that's the trajectory. We have the leader's dynamics, the input cost. We're gonna write, because it's the follower is gonna model using maximum trivial LQR, we can write down the distribution of followers, trajectories as a linear function of what the leaders do. Okay, now let's think about the objective. The leader might start with an objective that the leader wants to optimize. But in the case that leader does not know which hypothesis is correct, what we propose is say, well, instead of your original objective, let's care about this objective. So what does this orange objective says? It says, well, I'm going to measure the difference in the follower's response, the follower's trajectory under different hypotheses. Okay, and I want to make this difference as big as possible. That's why I'm minimizing the negative a bit. Okay, now if you have two hypotheses, you just maximize this one difference. That's fine. If you have multiple of them, then you have one difference per pair of the hypotheses. And our idea is to maximize the smallest one among all of them. Okay, in the worst case, I want all the hypotheses are as separate as possible. And maximizing the worst case distance is to make sure they're all nicely separated. What you can prove is that this optimization is what we call difference of convex programming. So you can solve it very efficiently using linearization and constraint convex optimization. And going back to the multi-polar problem that I started with, we consider a case where both the leader controls several dynamical systems. Each one is modeled using double integrators, and using the optimization problem that I showed you on the previous slide, we come up with this leader's decision to basically ask all the agents to go in as different directions as possible. So what I'm showing you here is the follower's trajectory distribution under different hypotheses. Okay, now because the leader make such a provoking choice, now if you observe what the followers do, you can quickly decide which one of the pile, which distribution is governing the follower's response. And when you combine it with Bayesian inference, you can quickly pinpoint which is the most likely hypothesis, as soon as you observe what the followers would do. For our future work, we really believe this framework that we propose will have a lot of interesting applications in both shared autonomy and mixed autonomy, where either a system driver is trying to infer the preferences of a human driver, or autonomous cars try to simultaneously infer at intersection what the other cars will do based on some prior hypothesis. So we heard a lot of interesting application and the new research within this context. So I'm happy to discuss future collaboration as well. And having said that, I'm happy to take some questions from the audience.
If your problem actually has a continuous hypothesis space, do you have any thoughts on how you might either handle that linearly or convert it into the
that is a good question. We have not considered continuous hypothesis space. I think the challenge in that case, you have to somehow partition, because nobody wants to deal with infinite dimensional objects, period. So you have to figure out some kind of clever way to partition your hypothesis space. And then if you can manage to do that, then some of these results are presented, they might be helpful in that case.
I also have a question kind of related to that. So you have a finite number of choices on basically the hypothesis. What happens when you increase that number?
That's a great question. So if you go back to this optimization problem, you can see that the number of terms in the objective depends on how many pair of hypotheses you have. So it basically increases a quadratic function in terms of how many hypotheses you have. You might need some like auxiliary variable to transform this non-smooth objective function to a smooth one. So that also depends on the number of hypothesis pairs you have. Nowadays, convex optimization is quite we can solve quite large scale, quite fast. So we're less concerned about that. It's not linear, so but it's quadratic. It's not exponential. So that's what I can tell you. Yes. So the assumption is the leader can have like a generic objective function. So we don't care about the leader's objective within this framework. So the leader's priority is try to figure out what the follower's type. The follower's objective function, this comes with the maximum LQR, is always a quadratic function on the trajectory that the follower is trying to optimize. And the leader's knowledge about the follower's objective is that there's a set of hypotheses, set of M1, M2, M3. One of them describe what the followers, well, one of them best describe what the followers would do.
The follower doesn't need to know the action that it wants to. He doesn't observe the new action. Because right now, it only depends on the state of the trajectory of the
Yeah.
I don't need to know the action, but I don't need to observe the action.
Beyond this point, yes.
Right, and then next we'll have a virtual presentation from Matthias Rowold from YouTube. Let me try to share a screen.
Can you hear me?
Give me 1 second. It's a little quiet. Can you try talking again?
Hello, test.
Yeah, you might have to speak up a little bit. It's a little quiet.
Okay, I try, but I cannot share my screen yet.
Can you try again?
Yes, now it's working. Okay, you should see the presentation now.
Yep.
Okay. Yeah, so I present a preview of open loop and feedback Nash trajectories in racing scenarios. And this contribution is still a work in progress, but I would like to share this outlook on future work we are going to do. And first, I want to briefly motivate the use of game theory in trajectory planning, and especially in racing scenarios. And yeah, the short answer is to make interaction-aware trajectories. Because the problem with sequential methods is that they first predict and then plan, and this is often very conservative and results in very cautious and even yielding behaviors in racing scenarios. However, in this shown situation here, the defending or the leading vehicle should defend its position, in this case, the blue vehicle. So the interaction-aware approaches, they combine the planning and prediction step so that they can leverage the knowledge about the other vehicles, for example, that they also try to avoid collisions. And this should then generate, in general, more progressive and even aggressive behaviors, but without becoming unsafe. And game theory is one domain that allows to combine this prediction and planning step. And then we usually define this trajectory planning problem, or we formulate it as a dynamic game with a joint state X. And the evolution of this joint state X does not only depend on on one player's control input, but on the control inputs of all players 1 to n. And each player has a strategy, and the strategy determines the control input at every stage K of the game. And also each player has a cost function, which is like in optimal control problems, often stage-wise defined. And it does not only depend on the strategy of player I, but also on the strategies of all other players. And in contrast to optimal control problems, we can not only minimize these cost functions for each player individually, but we try to find an equilibrium, and this is most often the Nash equilibrium. So no player can improve its outcome by changing its strategy unilaterally. And one feature of dynamic games is that depending on how we formulate such a strategy, we make assumptions about the information structure of the game, and this can result in different equilibria. And this brings us to the concept of open loop and feedback solutions. So in the open loop case, a strategy at stage K is just a constant function, and so the goal of finding a Nash equilibria breaks down to finding a control input sequence for every player. And in the feedback case, we assume that every player has access to the current game state X. So the strategy is a mapping from this current game state to the control input at this stage for the player. And an interesting feature of these concepts are that the open loop and the feedback solutions are in general different for non-zero sum games. And another feature that will be important later is that for games with linear dynamics and quadratic cost functions, we can calculate explicit solutions just like for regular LQR in optimal control problems. And given all this, our goal for the upcoming research is to find out whether the Nash equilibrium is an appropriate choice for non-cooperative racing scenarios. And if yes, is it better to follow the behavior obtained from the open loop or from the feedback solutions? And furthermore, we want to find out how robust these two concepts are against uncertain cost functions and players that do not behave according to the Nash equilibrium. So to answer these questions, we need to find a framework that is able to generate the open loop and the feedback trajectories. And solving dynamic games for trajectory planning, there are already many approaches exist, and we categorize them into these 5 groups. So we have, first of all, the generation of offline policies. Then we have sampling of many trajectory candidates and then solving for an equilibrium, for example, with bimetric games. Then we have the iterative best response algorithms that have been applied for racing already. And more recent categories are iterative LQR and methods that find trajectories that fulfill first order optimality conditions for the Nash equilibrium. And for our purpose, we have identified the iterative LQR methods, since they can be used to generate both the open loop and the feedback solutions of a game. And therefore, I want to explain this procedure in more detail. As the name suggests, the iterative LQ games, it's called, solves a non-zero sum game iteratively by approximating this game with linear quadratic smaller games. And beginning with an initial trajectory guess, the first step is to approximate or to linearize the dynamics. So from there on, we always consider the deviation from this trajectory. While the dynamics are linearized, the cost function is approximated with the second order Taylor series. And so we obtain a linear quadratic game that approximates the original game locally. In a backward pass, this linear quadratic game can be solved with a recursion that is very similar to time discrete LQR that we know from optimal control problems. And so we get a time variance, affine feedback law for every player. And here's the main advantage of ILQ games that we see. So by just changing this recursion, we can obtain the open loop solution as well. Then, of course, this big matrix K that's multiplied with the vector with the current state X becomes 0, so that the new control input does not depend on the state anymore. And there's no need to change anything else. So we only have to change the recursion. We do not touch the cost function or any other properties of this algorithm. And then finally, in the forward pass, knowing all the strategies of the players, we can update the trajectory, and the forward pass just applies this this delta U additive to the previous control input sequence and simulates the nonlinear dynamics forward and generates the new trajectory. And this entire procedure is repeated until there are no changes in the control input sequences anymore. We have already conducted a few simulations, and they show that we can indeed generate interaction-aware behaviors that consider the collision avoidance of the vehicles and of the opponent players. However, we also saw that this solution to which this algorithm converges heavily depends on the initialization of the algorithm and on the step size we use during the forward pass. And this brings us directly to the next steps. So we want to analyze this convergence properties further, but the main focus is still on the difference between the open loop and feedback solutions of the racing game. Another observation we made is that the cost parameterization can be used to adjust the aggressiveness of the ego vehicle, and this can be helpful when we, for example, want to distribute the responsibility for collision avoidance in different racing scenarios. And further things we want to analyze are the performance of the obtained behaviors when we apply this algorithm with a receding horizon, how this algorithm behaves when we have players that do not behave according to the Nash equilibrium, and of course we want to take into account more complex racetrack geometries and not only this straight racetrack. Yeah, and that's it from my side, and I'm happy to discuss here or either in the chat, or you can contact me via email.
Any questions from the audience?
I couldn't hear it.
All right, thank you. The next we'll have Nishtha. Let me make you co-host. Can you try to share the screen?
Hi, let me see. Can you see my screen now?
Yeah.
Okay. Just wait a second. Okay. Hello, everyone. I'm Nishtha Mahajan, and I'm here to discuss our work on intent-aware autonomous driving, a case study on highway merging scenarios here today. This is joint work with Professor Xiyang from the University of South Carolina. Let us first consider a scenario where we have a vehicle on the entrance ramp that is trying to merge onto a highway, and there's an incoming vehicle that could potentially block that entrance. Now, this incoming vehicle can either keep moving at its current speed or change lanes to accommodate the merging vehicle, or maybe it can act aggressively and speed up. Considering this uncertainty, the likely option for this merging vehicle is to adopt a conservative behavior. But by communicating the intent of this vehicle, there's an opportunity for collaboration between these two. Formally, SAE defines intent sharing as a class of cooperative driving automation wherein a sending entity shares information about its planned future actions for a receiving entity to utilize. It is important to note that this communication is one way, and the receiving entity does not have to accept it, but the sender is expected to execute this plan irrespective of what happens. To implement this idea, which we call intent-aware autonomous driving, there are three key questions that need to be answered. First, how can we computationally define and represent intents in this case? Given an intent, how can a sender comply with this intent? And how can the receiver utilize this intent? And third, how can the sender choose an optimal intent to induce this cooperative driving behavior? In this work, we try to address the first two questions. The third question is left for our future work. This gives an outline of the remainder of the talk. We'll be first discussing how to formulate intent sharing as a dynamic game. Then we look at how to implement this idea for highway merging, followed by experiments to investigate the potential of intent sharing. Let us consider a two-agent setting. Now, agent 2 shares its intent with agent 1, assuming that the world state can be factored into the local states of the two agents and an external state. The optimization problem for agent 2 is to maximize its expected rewards independent of agent 1, while also conforming to the intent that it has shared. On the other hand, for agent 1, the problem is to maximize its rewards conditioned on the entire world state, while also using the knowledge of intent that it has from agent 2. Now, to implement this idea, we consider a highway merge environment wherein the yellow vehicle on the highway shares its intent with the green vehicle on the entrance ramp. We have human-driven vehicles here in order to provide a realistic traffic scenario for these two agents. And next we'll see how we can represent these intents and how the AV2 can comply with this intent, and how AV1, that is the intent receiver, can use this intent. Now, intent sharing is inherently a commitment to comply with a shared intent. This can also be interpreted as a restriction on the admissible future behavior of the intent sender. With this idea in mind, we define intents as a vector of indicators specifying a subset of actions that the intent sender restricts itself to choose from, or in other words, commits itself to take. Now, we require that each committed action in this set has to be chosen at least once in order to avoid ambiguity between different types of intents. For this case study, we consider a 5-element action set representing high-level maneuver actions. And we also commit to this intent for the entire duration of a simulation episode. Given this action set, we consider 4 intents, as you can see on the screen. A point to note is that ideal action is always available in these intents for feasibility reasons. Given these 4 intents, we designed the policy for AV2 as follows. Firstly, we randomly assign an intent. Then, if the intent is idle, the policy is to just choose idle action throughout the episode. However, for other intents, we assign a random action trigger position, which is the position at which the other action in intent is executed. And this is a rule-based policy that we implement. For intent utilization, we consider a RL-based approach, wherein the state vector is represented by vehicle kinematics, that is the X and Y positions, and the X and Y components of velocities. For communication, we introduce an auxiliary state, which is equal to the intent if AV2 shares its intent with AV1 and null otherwise. For the rewards that the AV1 gets at each time step, we have 4 components, namely reward for high speed, reward for staying on the rightmost lane, a negative collision reward, and a merge reward. Now, this merge reward is further decomposed into 4 components, which account for a quick, safe, and efficient merge. Given this implementation and this testing environment that we show in this slide, our next step is to investigate if knowing the intent of AV2 can aid the AV1 in adjusting its behavior appropriately. With this in mind, we design our experiments with 2 scenarios, with and without intent sharing. And the policies for AV1 are learned using DQN. Looking at the performance of our learned policies, we can see that with intent sharing, not only is AV1 able to get higher rewards, but also the variation in rewards across different models is lesser. And moreover, we can see that the crash rate with intent sharing is 0, while we do observe crashes because of the uncertainty in AV2's behavior when intent is not shared. We further investigate visually how these learned policies look, and it's interesting to note that intent sharing enables the merging AV to effectively adapt to the intended behavior of the intent sender AV. For example, consider the lowermost row, wherein the AV was supposed to slow down. When intent was shared, the merging AV was able to exploit that information, keep moving at its maximum speed, and merge in front of this vehicle. But without intent sharing, because it was following a conservative behavior, it had to slow down significantly in order to merge. To summarize, in this work, we looked at intent-aware AD as a multi-agent decision problem. And using our implementation of intents, we demonstrate how the merging AV can use that information to appropriately adjust its behavior. For future work, directions can be explored. For instance, joint learning of this intent sender and the intent receiver agents, scaling beyond the 2-agent 1-intent setting that we have here, and exploring scenarios beyond merging, such as roundabouts and intersections, where interactions between agents is critical. Thank you. I'm happy to take any questions.
All right, thank you. Any questions from the audience? Yeah.
Hi, thank you for the talk. Have you explored or planning to explore any scenarios where the intention is not followed, where you essentially violate your first assumption that it is access restriction on the other agent?
Our plan is not to investigate it directly right now, but that is definitely an extension. If this commitment can have a probabilistic value, it will get more complex. So our focus right now is to look at this joint learning, but that is definitely possible using probabilistic commitments.
Thank you.
All right, thank you.
Thank you.
And then we'll have our last presentation of morning session from Rohan Chandra. Make sure I unmuted this. Yep.
Okay, let me just take this away. All right. So thanks so much for the organizers for putting this together and giving me the opportunity to present this work. It's a pleasure to be here. So my name is Rohan. I'm going to be presenting decentralized multi-robot navigation using Game-Theoretic CBS. This is joint work with the wonderful collaborators at UT Austin. So So just to set the stage for the talk today, because this is a relatively shorter talk, so I'm going to put more focus on the introduction and lesser focus on the methodology. I'm going to talk about the key idea, and I'm hoping that that creates enough of an intrigue that motivates all of you to go and read the paper in more detail. But I'll focus on the introduction and the key results, and I'll sort of leave you guys with the key ideas. So that's sort of the agenda for today. So beginning with the introduction. So my research broadly focuses on focusing on algorithms and systems to enable robots to navigate safely and efficiently among robots like among humans like humans. So I'm focusing on creating this like a human-like mobility framework, and some of the grandstanding challenges that I'm currently focusing on that excites me are autonomous vehicles and very, very complex traffic, the kind of traffic that you might see in developing nations like India, last mile delivery service robots, and personal home robots, right? And even though we've seen some tremendous progress in these areas over the years, we've still not gotten to the point where we can confidently and safely integrate these robots into the fabric of human lives, right? And as humans, we can do all of these applications because humans move in very diverse, unique, and complex ways, but robots cannot do this. And what do I mean by that? I mean that even though robots can navigate autonomously fairly decently and reasonably well, they cannot do tasks like they cannot go and pick up our groceries and order and go and shop for groceries. They cannot run through a crowded airport if they wanted to go and attend IROS and they're late for the flight. They cannot run through a crowded airport. And finally, they cannot drive in general traffic, right? Like you have Cruise, you have Waymo, they can do all these kinds of driving, but you need to geofence them, you need to do all kinds of mapping, you need to train them on millions of miles, you need to create simulations on all of that stuff, but they cannot drive in general traffic, especially in like New York or India. So there are a bunch of challenges that plagues these robots when it comes to deploying them and trying to deploy them in shared human environments. Like there's a problem of safety, there's a problem of uncertainty, robustness issues, adversarial issues. But one of the issues that I focus on in this paper is the freezing robot problem, which is when faced with a dense and a dynamic scenario, then due to a lack of feasibility or lack of available feasible actions, the robot may just freeze and enter a deadlock. So how do we resolve this problem of the freezing robot problem is part of the research question, which is how we can design a navigation algorithm for multi-agent scenarios that is provably safe, provably deadlock-free, and fully decentralized. So I'll put out a disclaimer that this work is a little bit different from little bit tangential to the theme of the workshop, in that I'm not solving a dynamic game. I'm modeling it as a partially observer stochastic game, but I don't like solve like for one of the solution concepts that was presented in the talk before the last one, using techniques like iterative best response or direct formulation. So I don't use all of that, but I do model it as a partially observer stochastic game. I'm not going to go through all of these variables. It's a fairly standard formulation. One thing I do want to highlight is that there are K agents. It's a multi-agent game. There are K agents. It's a finite horizon, so T is the horizon. But one thing that I want to highlight is that each agent has a set of preferred trajectories. So this gamma I tilde indicates that it's a finite set of preferred trajectories that each agent has that could be defined by the min path, min jerk, min time, and what have you. But we assume that each agent has this set of preferred trajectories. Now, in order to solve this POSG, we use a very standard concept of the optimal control objective, where we are seeking to find this policy pi I star, which is essentially trying to minimize the error between the planned trajectory xit of the agent of the ith agent and the preferred trajectory. So we're trying to minimize the error between the planned trajectory and the preferred trajectory over a finite horizon t. And it is subject to these constraints, which basically convey or they basically involve the feasibility, with the boundary value conditions, the safety and the collision avoidance, and so on. So this is our optimal control objective. Now, what the problem is, and what actually causes a freezing robot problem, is that there exists a finite duration. There exists some duration between A and B in this game, in this interaction, where the preferred trajectories, there will be at least one pair of agents, ij, for which all the preferred trajectories of I will be in conflict with all the preferred trajectories of j. So this optimal control objective is not easy to solve. The solution is infeasible. So that is what mathematically leads to the freezing robot problem. And I don't intend to go into the definition at all, but what this loosely is saying is basically that the preferred trajectories are in conflict with one another. And our solution concept and the key idea is how we can perturb the agents, how we can perturb the agents or the state space of the agents in a way such that we can resolve this conflict. So we employ a bi-level optimization control objective where the top level corresponds to perturbing the state of each agent onto safe and deadlock-free regions. And I'm sweeping a lot of math under the rug as to what are these regions and how we can construct them. But the idea, or the high-level idea, is you resolve this conflict that I talked about in the previous slide. But you resolve this conflict by perturbing the agents, and this perturbation is fully decentralized. It's autonomous. You perturb the agents onto the safe and deadlock-free regions, and you use control barrier functions to lock in guarantees via forward invariance. Once you do this perturbation optimization, then the bottom level kicks in, and it solves the motion planning problem, which is the optimal control optimization I showed before. So these are the two steps that they happen, and whenever the agents detect that they are in sort of like in a danger zone, in a deadlock zone, or they're about to enter a deadlock, they do the perturbation, they enter into the safe and live deadlock-free zones, and then the CBF ensures the forward variance. So just to quickly go over the results, let's not look at the numbers too much, but what I'm essentially comparing is I'm comparing a bunch of deadlock resolution methods, and I am comparing them according to the metrics average delta velocity, path deviation, and wingspan ratio. So the average delta velocity and path deviation measure how smooth the resulting the trajectories are after the perturbation. So the lower the average delta velocity, the lower the agents have to modulate their velocity, the better it is, because it's minimally invasive in that sense. And the lesser the agent has to deviate from its preferred path or the path that it is on, the better it is. The make-span ratio is the time taken by the lead agent divided by the time taken by the last agent. And we find that our deadlock resolution is the smoothest compared to the other deadlock resolution methods in the literature. We also compare with other navigation baselines. These are navigation methods that may not necessarily do deadlock resolution, like they may not necessarily give guarantees on it, but they are decentralized navigation algorithms, and these are results of these methods in simulation, which I then rendered in this visualization. And finally, I'll show, may not have enough time to show all the results, but hopefully I'll show like a couple of the scenarios. So this is, first one is the baseline, which is human passing through the intersection, expecting the robot to yield, but in the baseline, the robot collides. And here is our game-theoretic deadlock resolution approach. It anticipates the human and yields to it. So here the human deliberately tries to be cautious. Here's the expectation is that robot should speed up once it sees the human slow down a little bit. But as you can see, like it enters a deadlock and waits for the human to back up and wait for it to pass. And here we can see the robot speeding up. And finally, we have a doorway scenario where again the expected behavior is for the robot to yield, but it again collides, and in the game theoretic solution, the robot will yield. Okay, and that's the end of my presentation, and I can take questions. Thank you.
All right, any questions? Yeah, go ahead.
The deadlocks are resolved pair of agents at a time. Correct. You get over deadlocks. So my question is that to resolve the deadlock, can you modify the trajectory of this may generate another conflict with another agent, right?
Yes, so we yes, we run into scaling issues. So we've done it with 2 agents and 3 agents, and we started to run into problems with more agents. But the idea is that we're explicitly focusing on tightly coupled interactions. That's the target area. And when you think about dense crowded areas, you typically are engaged in tightly coupled interactions with few agents at a time, right? Even though the scene might itself be dense, but at any one point of time, if you're engaging in a doorway scenario or hallway intersection, right, the interactions would be like on a micro scale, where you would be interacting with 1 agent or 2 agents at a time. So that was our entire philosophy. But we do recognize that there is a scaling issue with our approach here. Thank you.
Okay, let's give Rohan a hand.
So just 2 quick announcements before we break for lunch. So let me just switch back to. Yeah, so just the plan for post lunch will be that once we have we'll be back in this room just right before 1:20, and then we'll have our second session for the invited speakers, and we have 5 talks, then followed by the coffee break, followed by our second session for the contributed talks. So just another just for fun, because we are all here in person and we're still, COVID has not left us, but I just want to take a group picture over here, and then we can head out for lunch. And the other thing is also at lunch, if people want to meet together, that's the whole point. So maybe we can just come up front here, and I'll yeah, we'll take a quick picture and then head out. We don't want to.
Yeah.
Thanks so much. Yeah. You'll be here for the entire day. Yeah. Thank you.
Yeah, really. Yeah. Come on, let me get inside.
Maybe layer us a little bit. If you can step right behind it. Get tall enough so it can. This is good.
Okay, good. Thank you.
Actually, can you check that they're already there, and I'll check. I'll show up maybe 10 minutes before.
Okay.
To go over, make sure that.
I'll
because it's a Mac or sometimes Mac.
is it a PowerPoint?
Yeah.